Okay, we're given that f of 8 equals 9 and f of 9 equals 4. We want to find f inverse of 9. There are two ways to do this. One way is, let's go ahead and make a table listing what we know about the function. We know that f of 8 equals 9, so we have this. We know f of 9 equals 4, so we have this. So we know that f inverse just reverses the columns here, and we end up with 9, 8 instead of 8, 9, and 4, 9 instead of 9, 4. And this tells us that f of 9 equals, f inverse of 9 equals 8. And also f inverse of 4 equals 9. Now, we can write all this down. We see that f inverse of 9 equals 8, f inverse of 4 equals 9. And then we can simply note that this row of this table tells us this, which is our answer. Alternatively, if f of 8 equals 9, then f inverse of 9 equals 8. So we just write f of 8 equals 9, so f inverse of 9 equals 8. And also we write this, f of 9 equals 4, so f inverse of 4 equals 9. And we notice that we have our answer right here, f inverse of 9 equals 8. Over here, we have a problem stated in terms of a window. So you're given, without the labels, that x equals 0, x equals 6, y equals 0, y equals 12. You're given this graph of a function. Okay, well, you're told that the x window runs from x equals 0 to x equals 6, from 0 to 6. So you say, okay, well, this is x equals 0, this is where x equals 6. And similarly, you're told that the y window runs from 0 to 12. That means y equals 0 down here, y equals 12 up here. So here's your window, and now you can estimate the coordinates of any point within this window. So if you want to estimate f of 2, well, that means the value of the function f when x equals 2. The value of the function is the y coordinate. This is y equals f of x. So if x is 2, you find the point on the graph that corresponds to x equals 2 during a projection line. And then you project over to the, here's where x equals 2. You find the value of y where x equals 2. You find the point corresponding to x equals 2. And then you estimate the value of y, and that's your f of 2. That's where y equals f of 2. And you estimate that as 7. You got the interval from 0 to 12, you subdivide that in half, you get 6 about here, and then you have 9 halfway here, so you have 8 and 7. So you say, y is about 7. Okay, so we've estimated 2, our projections show us that f of 2 is about 7. And then we're asked to solve the equation f of x equals 6. Well, f of x is your y value. If f of x equals 6, that means you have to have a point that where the y value lies along this horizontal line, y equals 6. We see where that line intersects the graph, and you see that it intersects at this point, and this point has x coordinate. This is 1 and this is 2. So I estimate that's about 1 1/4 or 1.25. So f of x equals 6 for this value of x. This value of x we estimate to be 1.25. Projections then tell us that f of x equals 6 when x is about 1.25. So the solution to the equation f of x equals 6 is x approximately equals 1.25. Now there's a question about a slant asymptote. It's not something that's going to appear on the exam, but it's something that we're going to look at next week, most likely. So we have the function f of x equals x squared plus 0x minus 36 over negative x, 4x minus 6. Okay, we rewrite this, multiply the numerator and denominator by -1, because we don't really want a negative on our leading term of the denominator. Better to have it on the leading term of the numerator. And we get this. 6 times So there is a slant asymptote. Now your rule is if the degree of the numerator is 1 greater than the degree of the denominator, you're going to have a slant asymptote. We're going to see why that is in terms of this example. Okay? The degree of the numerator is the degree of the denominator plus 1, or the degree of the numerator is 1 greater than the degree of the denominator. To find the slant asymptote, we do a long division. We just divide this into this. Because the degree of the numerator is 1 greater than the degree of the denominator, when we divide the 4x into the leading term here, we're just going to get a linear term, just an x. 4x goes into negative x squared how many times? Negative x over 4. This is, of course, because negative x over 4 multiplied by 4x gives you negative x squared. Okay, multiplying the negative x over 4 by the 4x minus 6, we get negative x squared plus 3/2 x. We subtract these from the corresponding terms in the original numerator, and we get negative 3/2 x. We get a 0 here and a minus 3/2 x here. Now we have the 36, so we want to divide this into negative 3/2 x plus 36. We do that. We get negative 3/8, and check that. Negative 3/8 times 4x is negative 3/2 x. So this will subtract off and give us 0. And 3/8, negative 3/8 times negative 6 is negative 9/4. Then we subtract the negative 9/4 from the 36. We get 36 plus 9/4, which is 153 over 4. Now we divide the 4x minus 6 into 153 over 4. We get this term, 153 over 4 divided by 4x minus 6, and that's the end of our long division. Now, we can then write our quotient, which is, this quotient is our original function, just put in different form, and we can write it as, well, the negative x over 4 minus 3/8, I factor out a negative 1/4, I get negative 1/4 times x plus 3/2. You can multiply through by negative 1/4 and see that you get this. Plus 153 over 4, if I did my arithmetic right, is 38 1/4, 38.25 over 4x minus 6. If I want an integer up here, I multiply numerator and denominator by 4. I get 153 over 16x minus 24. And maybe sometimes you want to do that, but it really doesn't matter. You see then that what we have is a rational function here plus a linear function. This is just a straight line graph, slope negative 1/4, y-intercept negative 3/8. Okay? Now this rational function, as x gets big, this approaches 0. It's obvious. The denominator gets big, the numerator stays 38.25. So if the denominator is 1,000,000, this is almost 0. So for large values of x, this function is going to equal this. And this is just a straight linear function. For values of x near the 0 of this thing, which is at 3/2, this thing's going to blow up. You're going to have a vertical asymptote in this rational part. Okay? So you have this rational part with its vertical asymptote, but then when you get away from that and get far away from that, you approach this linear function. So this linear function becomes an asymptote. Well, that linear function slants, so that for large x, the graph is going to approach that slanting line, and that's what you mean by your slant asymptote.